All right, thanks, Ashley, and thanks everybody for attending the presentation. Today I'll be presenting on Great Lakes Coastal and Nearshore Benthic Mapping. Next slide, please. So just a quick virtual introduction for those that may not be familiar with who I am. So I'm a physical scientist with NOAA's Office for Coastal Management, Master of Science in Geography, Bachelor of Science in Geography. And where my interest really lies is providing remote sensing, also artificial intelligence and machine learning, and geomorphology expertise to the office and our partners here in the region. And one of those fun facts, fishing, canoeing, camping, and time with the kids, and of course enjoying the Great Lakes as well. So with that said, we can go to the next slide. So similar to Charles, NOAA's interest, especially through the Office for Coastal Management, ties into a lot of different aspects. The Office for Coastal Management is looking at everything to help keep our residents safe, supporting the economy, as well as our natural resources and the function of those natural resources. We're trying to keep all these different things in unison, in harmony, I guess, in some regards. So while we're not the ones responsible for the full implementation, that does fall back to our state partners, and we depend heavily on those state partners. We do provide oversight as well as technical assistance. And my role here in the Great Lakes region is doing exactly that, providing that geospatial technical assistance to partners across the region. And so we do get brought in to look at things like benthic mapping, data collection, and other geospatial activities day to day across the Great Lakes region. Next slide. So, the first question that I often get asked is, haven't the Great Lakes already been mapped? And, certainly we can go all the way back. This is one of the first maps created for the Great Lakes from 1755. And, they did a pretty okay job of getting the shape of it. But you'll notice too, if you look at this, for example, in Lake Superior, we see islands that are on this map that just do not exist. And so if we just take that saying, that, hey, we've mapped the Great Lakes, we're done, we don't need to do any more work, we'd be losing a lot of what is happening out there underneath the water. So I think it's really important to reiterate the reason why we go out and we do these mapping and data collection efforts within the Great Lakes. And if we go to the next slide, we know, based off of the Interagency Working Group on Ocean and Coastal Mapping, the work that Meredith and others have been putting together and calculating, just how much of each of our regions have been mapped to meet modern mapping standards. And again, when we talk about modern mapping standards, that's one sounding or 1 point measurement within a 100 meter by 100 meter grid cell. And that data needs to be current. And again, what we mean by current is anything that's been collected from the 1960s to present. And again, what's scary is that we've only got 5% of the Great Lakes region that meets that standard. And if we go to the next slide, and I saw this picture yesterday, in the first presentation by the keynote. And what's interesting here is you look at the other parts of the nation, so the eastern seaboard as well as the western seaboard, and you could literally fit the Great Lakes region within that 3 or more soundings per 100 meter grid cell off the eastern seaboard, for example. And so we definitely have a long way to go, and I definitely appreciate the stats that Charles provided in that, we basically need to be collecting 4,000 square nautical miles of data per year in order to meet that 2030 requirement. And so we've also seen, though, too, that there's been a lot of efforts to work towards that goal and meeting these requirements. And so if we go to the next slide, I will say this, though. From the standpoint where we're working, there is one big caveat. And if we go to the next slide, that is, bathymetry doesn't always equal benthic mapping. And what I mean by that is, while we're meeting the standards for modern mapping in terms of that one sounding per 100 meter by 100 meter grid cell, we're not necessarily doing all the benthic mapping within those cells as well. And so that's what I want to present on today, is the efforts that are underway to improve not only a better understanding of our water depths, but also what's existing on the bottom. And we saw some great presentations yesterday by Jamie Hoover and Nathaniel Penrod in the work that they've been doing using BREST and CMEX in the National Park Service lands. What I want to touch on today is some additional work that's going on across the Great Lakes region to address this benthic mapping, and how it is really only a fraction of that 5% that we're currently doing to support benthic mapping. Next slide. So there's a quote that I share out quite a bit, and that is this one by Heyman and Wright, and the fact that marine environments and their associated biota are dictated by the physical, oceanographic, and geographic settings at all scales. And so whether we're looking at some of the coastal erosion and its impacts to the nearshore environment, the urban settings, or in this case in the lower right, where we see invasions of Dracidian mussels and Cladophora and the impacts they have on the biotic, it's really important to get a sense of what this environment, the physical environment underneath the water, looks like, and its relationship to the geographical settings in which each of those are present. Next slide. And this ties into a lot of different initiatives and factors of life in the Great Lakes. Here's just one of the examples from the Great Lakes Fisheries Commission, and that the commercial, recreational, and tribal fisheries are valued at more than $7 billion annually. When we look at the Great Lakes Restoration Initiative and the focus there, when you look at the species, for example, that may benefit under Action Plan 3 of GLRI, you see lake trout, you see brook trout, native freshwater mussels, native prey fish, lake sturgeon, but then you also see other species that may benefit from a better understanding of the substrate and benthic environments, including wild rice, piping plover, and other marsh birds as well. And as I mentioned, we are seeing invasive species coming into the Great Lakes, and from the US EPA, there are at least 25 invasive animal species. And again, these are just animal species. We're not even talking about, some of the other vegetative species that are present. And so how they are impacting this benthic environment is really important to understand. And the other point I didn't put on this slide, but I should have, is having a sense of what exists out there prior to any type of disaster that should happen. As we've all heard about the exercises and having the studies to understand what might happen with, say, a Line 5 breakage or other contaminant entering into the Great Lakes waters. Next slide. And so the reason I'm focused primarily on the coastal and nearshore environment is because it is one of the most dynamic and complex to understand. It is that interface between the land, the water, and the air. And unlike other nice warm tropical locations like the Caribbean or the Pacific Island territories, we also have a very limited window in which we can successfully operate and collect that data. But there are also a lot of new technologies coming online that are allowing us to collect data outside of our typical field season, as well as improve the understanding of our benthic environments as well. And so first and foremost, I do want to acknowledge that topography and bathymetry are those foundational data sets that are helpful for understanding our coastal and littoral environments. But we do also need additional data sets to help support that need. Next slide. And so luckily, I will say that we are in the age of exploration still in some regards, because we do have these new sensors and platforms that are coming online every day. We've seen the presentations on the LiDAR data, either being airborne as well as satellite-based with ISAT-2, but also the utilization of drones to start collecting this data as well. We've seen echo sounders being placed on vessels, underwater, unmanned or unoccupied or uncrewed vessels and vehicles, as well as the support of imagery to include airborne hyperspectral, multispectral, and satellite imagery to help in those coastal environments. And the last and not least, those in situ measurements, they're really important to see what's happening directly in the ground or below the surface in the substrates. And so drop cameras, ponars, ROVs, and again, the use of these uncrewed underwater vehicles are so important to helping understanding our Great Lakes. Next slide. And so, when we start to think about how to get started, it was great to see that we're starting to see more and more presentations in the utilization of CMEX. The beauty of CMEX and how it can be utilized. We talk about the mapping standards in terms of, one sounding per 100 meter by 100 meter grid cell. CMEX is the standard in which you can think of it this way, that everybody can be a musician. They all write their own music. But the beauty of using, music in terms of bars and notes is it's a standard in which allows one user to take that data and apply it to another use case. And so that is the beauty of CMEX. Next slide. So CMEX stands for the Coastal and Marine Ecological Classification Standard. It is a Federal Geographic Data Committee standard, and as such, anybody that receives federal funding should be using the standard if they're doing ecological or benthic habitat mapping. And so we saw the presentations yesterday by Jamie and Nathaniel where they are looking at that geoform component quite extensively. And what I want to highlight today is some of the work that's been done on substrate and biotic components as well, in terms of understanding the physical as well as the biotic makeup of our substrates in the Great Lakes region. The other thing that I will say too is this is the first comprehensive federal standard for classifying and describing coastal and marine ecosystems. And it is modifiable to meet different user needs. And then the other thing I do want to highlight today as well is it's currently undergoing a rewrite to incorporate new information and data to help in modifying the standards to meet multiple and more needs that weren't initially addressed in the first revision of the standard. Next slide. So just for example, we wanted to look at how CMEX could be applied in the Great Lakes region. And I do want to highlight that there has been some amazing work done previously to start in cataloging and classifying the Great Lakes. And there's a lot of great data and resources available through the Great Lakes Aquatic Habitat Framework. And that is the data that you actually see here on the left. This is the substrate data set currently available. And you can see that it is very generalized, but what's nice about it too is it covers the entirety of the Great Lakes region. It may not be at though a scale where somebody's working at a project level and understanding, for example, here, the spread or the habitats for Cladophora and Dracidian mussels. And so the orange areas on screen there in the left are what are identified as coarse sand. And then what you can see on the right is where we've gone in with the CMEX classification using topography LiDAR, satellite imagery, multi-beam echo sounding data, side scan sonar data, and as well as drop cameras and sediment grabs to help with refining that to create a CMEX classification for both the biotic component and the substrate component at a minimum mapping unit of 10 meters by 10 meters squared. Next slide. And we're starting to see progress being made. On this map is actually highlighting geographies where CMEX mapping or benthic mapping has been completed, including Western Lake Michigan by NCOS, some of the work in Green Bay and Eastern Lake Erie through our organization, work at Illinois Beach completed by the Army Corps of Engineers, and the work at Sleeping Bear Dunes at South Manitou that's being completed by the National Park Service as well as through our office as well. In addition, you'll see white pins on the map here highlighting geographies that are currently undergoing work, including Thunder Bay and some of the work that has been presented to date on that. Again, the Sleeping Bear, which I'll be touching on momentarily here, the work that Nathaniel highlighted yesterday at Isle Royal, and some ongoing work at the Apostle Islands. Next slide. So for 2020, we received GLRI funding to go out and do benthic mapping on the western side of the Apostle Islands, in particularly the western side of the Bayfield Peninsula between Bark Point and Sand Island. And this was our first use of a multi-partner approach to doing benthic mapping. And so we work very closely with NOAA NCOS, the National Park Service, as well as our contractors, Wolpert and Dave Evans and Associates. to go out and collect data. And sorry, I should also mention NOAA GLERL for the vessel support and crew that did the actual on-the-ground data collection here. And so in 2020, they were able to collect all the data that you see now on the graphic in the right. And from that data, NOAA NCOS is now going out and they've actually just completed field validation, but are starting to work with that data to develop the CMEX classification for both the geoforms and substrate components, and the biotic if possible too, with the available data from here. And it not only includes this multi-beam backscatter data and bathymetry, but also a bunch of ancillary data that's been collected by US EPA, National Park Service, USGS, and other agencies to help with understanding the composition of the benthic habitats present here along the shoreline. Next slide. In addition, for 2021, we asked partners about where they'd like to see us go next, and Sleeping Bear Dunes was a geography that continued to get a lot of need from state partners as well as federal partners. And so we started to ask, which geographies would be suitable for data collection to include not only multi-beam echo sounding location, but expanding upon the Jabaltek's topobathy LiDAR coverage and actually flying a bathy LiDAR sensor over this geography. And so the map on the left are the priorities as identified by the partners. And then the map on the right is showing where we wanted to get additional bathy LiDAR acquisition completed. And so if we go to the next slide, this was what the coverage looked like in terms of high resolution bathymetry in the Sleeping Bear Dunes area prior to the 2021 field season. And if we go to the next slide, this is the updated coverage based off of where things stood as of September 23rd of this year. And so you can see that we were able to get a lot of the area we had anticipated with bathy LiDAR coverage, and we can actually thank the mussels for improving water clarity here. We were getting down to about 25 meters water depths with the bathy LiDAR sensor alone. And then utilizing the RV Laurentian as well as the RV Echo, they are out in the field still, are working to fill in the remaining coverage here as well. And so between these two data platforms, we do have some areas of overlap that allows for seamless integration of both data sets together, but then also to look at things like how the backscatter compares to the reflectance from the bathy LiDAR sensor. There's a lot of interesting new features that are coming from these data sets, and we look forward to sharing it out to partners once it's undergone review by our staff and QA/QC. And again, as Charles mentioned too, understanding too, there may be culturally significant sites within this area as well. So that will have to undergo a review of from additional purposes in that regard prior to being publicly released. Next slide. So a lot of the work I just highlighted was on using multi-beam echo sounding and its derived products for classification. But that's not the only platforms that we can leverage. And so I also want to highlight some of the work that we've done with Molly Reef and the Army Corps of Engineers, as well as Steve Brown and Ethan Thuracomp at Illinois State Geological Survey. And Ethan is actually now at Michigan State University. But if we go to the next slide, for this work, we actually used airborne and spaceborne products and derived products for the benthic classification off of Illinois Beach State Park. And so what we were able to use in terms of airborne products from panels A, B, C, and D include the bathymetry derived from bathy LiDAR. B is actually the water leaving reflectance from the hyperspectral CASI 1500 sensor that flies together with the topobathy LiDAR. C is a normalized reflectance based off of the LiDAR, and so it's basically combinations of panels D and B that make up that C panel, and D is actually the reflectance from the LiDAR itself, and so we can use all those products to help with benthic mapping from an airborne standpoint. The satellite products include A, which is the multispectral, in this case it was Sentinel-2 satellite imagery, B is the depth and variance indice created from that imagery, and C is actually the satellite-derived bathymetry generated from a combination of the imagery itself from the satellite, together with some of the LiDAR depth measurement points. And we'll describe that on the next slide. Next slide. And so, using the satellite data, we can help that fill in some of the LiDAR gaps, and then in turn use the LiDAR data to help improve the empirical regression in helping to develop the satellite-derived bathymetry. It's not as straightforward as it might seem. We did use the Send-to-Coral toolbox available through the SNAP desktop software, and it was interesting to see some of the spatial patterns present within the data as well. And so when we look at satellite-derived bathymetry compared to the LiDAR bathymetry, there's a pattern that we see where, in the deeper waters, the satellite-derived bathymetry overestimates the water depth, and then of course in the nearshore, it underestimates the nearshore depths. And so this is something to take into consideration if you try to go, one platform over another for doing this nearshore coastal benthic mapping work. Next slide. And so from those products, we looked at a lot of different, even the order and how those products are fused together. And this is just here to show the overall accuracy as it relates not only to satellite versus airborne, but how they map out for different types, whether that be coarse substrate, fine substrate, or then even anthropogenic substrate, which only the airborne, for example, picked up in terms of some of the road beds that are currently underwater. And then also too, looking at vegetative beds, in this case, looking at Cladophora and its presence. And again, how that compared between the airborne and the satellites in terms of biotic responses being picked up from the satellites versus airborne products as well. And so overall, the accuracies anywhere between 88 to a little over 95% for overall accuracy, and producer accuracy varied all the way from 0 to 100. And so it's really important to look statistically at how these products perform in their overall classification. And again, this is where the work with Stephen Brown and Ethan Tharakoff was very valuable in getting a lot of that ground truthing data to help with validation of the mapping products for CMEX in the end here. Next slide. And so just some additional considerations to think about, especially when we talk about coastal and nearshore mapping in the Great Lakes. Obviously, water levels and the change is something to consider. So if we look at that period of low water levels back in 2013, what was topography? Next slide. Is now bathymetry. And so it's really important to, when we think about coastal mapping, to include the topography and the nearshore environments when we think about mapping, because these are those dynamic areas where things do change over time. And if we go to the next slide, it is surprising when we think about benthic mapping in time. I mentioned at the start of my presentation just how dynamic our nearshore and coastal environments are. And if we look here in a span of just 10 years at Illinois Beach State Park, the amount of erosion that's been present, so we can see it in the imagery, what's happening in terms of the shoreline being eroded and washed away. But what's really impressive with the LiDAR and multi-beam data is we can now see also too what's happening in the nearshore environments, in coastal environments, in terms of not only how that area that's eroded is now being transported along the nearshore through littoral sediment transport, and then also too looking at bed scouring that's occurring along our nearshore environments as well. Just above the two circles on the bottom there's a water intake pipeline, and you can see that with the predominant north to south currents here, how that bed scouring just to the south of that water intake pipeline has occurred in this 10-year window as well. Next slide. So lastly, a lot of this work couldn't be done without all the partners that we depend on. And again, I mentioned that we work very closely with the coastal zone management programs, as well as our reserves, so the National Estuarine Research Reserves. We have 2 currently established, and 1 coming online, as Charles mentioned. Green Bay will be getting a National Estuarine Research Reserve coming online here soon. And so, it's not only the state partners and our reserve partners, but if we go to our next slide, It's also all the other federal partners and NGO partners as well that help to make this a strong effort in the Great Lakes. And so we're really appreciative of the opportunity to work with every one of these agencies in the Great Lakes. Next slide. And so just wanted to highlight some of the resources that are available. And again, when this is available offline, these links should be interactive, so you can click on them and go to each of them. I mentioned the work with Molly Reef. The last link is actually a link to an article in the Journal of Remote Sensing that's highlighting that work that has been done at Illinois Beach State Park. Next slide. And lastly, just a big shout out and a big thank you to, the guys and gals that are running the vessels and doing the data processing. We definitely are appreciative of all the partners that are working to make this effort happen in the Great Lakes. And again, thank you so much to the Great Lakes Restoration Initiative and the funding provided to ensure that we can continue this great work. Next slide. So with that, I will take any questions.
Thank you so much, Brandon. Great presentation, and I'm seeing that Jay is giving you a high five in the questions as well. David Clark has a question. Brandon, you mentioned CMEX habitat mapping of Southeast Lake Erie is complete. Where can we access those finished products?
Yes, so those products are finished and we're working to get those pushed up onto NOAA's Digital Coast at the moment. So just need to wrap up some of the metadata records and get that posted.
Okay, great. I wanted to ask you, Brandon, one of the things we say about CMEX a lot is that, it's living, it can be improved. And I wondered, in what you talked about and demonstrated today, were you actively thinking about modifications to suggest, or
yeah,
how is it working with CMEX,
Yeah, no, great question, Ashley. So yeah, through Ashley's website, through the IOCM website, there is a CMEX webpage, and there are a few links online there to actually connect with and email the CMEX folks with any of your suggestions or recommendations. There's also there's a working group through a USGS Confluence page, and I'll be happy to provide that link after the presentation here, where people can weigh in and provide additional feedback. If you are mapping and using the standard and something's just not in there, one of the things that we actually recommend is behind anything that you're interested in proposing, you can actually map it into those products. And what we encourage is actually adding a parentheses P and something that's being preliminary or promoted to CMEX. And so when we look at those products, we can then say, hey, here's something that we didn't think about putting into the standard. It's being mapped, and so can we put that into the revision for the standard moving forward? So whether you're actively mapping now or want to weigh in on that, there are multiple different avenues allowing people to provide that feedback, actually.
Okay, Brandon, great. One more question, I think, before we have to wrap this one up. Is the mapping referencing a datum such as IGLD or LWD?
Yeah, so
Water?
we don't really, like I said, we're right now just focused primarily on the substrate component and the biotic component and the geoform component. And while bathymetry values themselves don't necessarily show up in the final products, in the metadata records, we do encourage folks to acknowledge which vertical datum they are using for those input products in creating the CMEX, the end result CMEX products as well. So that usually is attributed to the source data that's coming in. That doesn't really equate out into the final CMEX products themselves, unless, again, there's something that you're specifically calling out in regards to, say, water depth or bathymetric elevations.
All right, we're going to squeeze one more question in because Peter sent in a good question. With many disparate CMEX and consolidated mineral substrate mapping efforts going on, it seems like there's a potential for classifications at different resolutions, such as some groups including mixed classes. What is your vision for an eventual Great Lakes harmonized map, and is it likely to arrive at some lowest common denominator like coarse and fine?
Great question, and that is the beauty of CMEX as well, is it does have a hierarchical classification in terms of the schema. So, you know, as we talk about fine and consolidated, and again, that's geologic fine unconsolidated substrates, you can get into, you know, the percentages even. You know, if you go and do a sediment grab, you know, what percentage of is it sand, salt, clays, in terms of the sediment percentages. And in the case with Molly Reef, we actually did have to go back up. So we thought we could go down to a very fine level of scale, but because it's nested in this approach with CMEX, we can actually go back up a tier in that regard. So I think that does help with some of the harmonization, because not everybody's collecting to that level of detail, or the sensors aren't getting to that level of detail. And so, for example, getting back to the paper, and again, that could be an entire presentation on its own. For example, the satellite, we had to stop at the subgroup, whereas with the airborne, we could go to a higher distinguishing of the substrate types itself. So I think in the end, you know, we can start to think about how best to roll those up to get to that harmonization piece. But yeah, certainly great question, Pete, and I think that's why it's important to have multiple partners involved with those discussions going forward.